In this slide, we will show an example for the single application of the Simpsons 1-3 rule. And we want to use that for the same function that we use for trapezoidal rule, this function with fifth order polynomial. And we want to get the integration of this between a equals 0 and b equals 0.8. And remember that the exact value was this, so we can check the true error as well. And because we will apply the Simpsons 1-3 rule, we need the limits a and b and fa and fb, as well as one middle point. So that one middle point means that our h will be 0.4. That's why actually we will have, n equals 2 for Simpsons rule, because we need that middle point. Then b minus a divided by n is equivalent to 0.8 minus 0 divided by 2 equals 0.4 is h, we can say. Then we will start again a equals 0, which means x0 is 0, and for that fx0 or f0 is 0.2, and then we add this h 0.4 for x1 is equivalent to x0 plus h equivalent to 0.4. Then f0.4 is 2.456, and for x2 it's actually x1 plus h, which is 0.8. 0.4 plus 0.4, and f0.8 is equivalent to 0.232. By using these three, we will use a parabola function of the integration, this one. Let's use it here. The integration is equivalent to b minus a, meaning 0.8 minus 0, and fx0 is 0.2 plus 4 times 2.456 plus fx2 0.232, like this, divided by 6. From here, the integration value is 1.367467. So this is the approximated integration, and this is the true integration. You can see that we approached it very well, even though we use a single application of it. If you remember, in the trapezoidal rule, it was so far away from the actual value. And if we calculate the true error, it's just 1.640533 minus 1.367467, which is 0.2730667. And you can calculate the true error as well by dividing this by the true value, and you can divide it by yourself. I'm not going to write it down here. 16.6%. So this is very small, as you can see. In the single trapezoidal rule, this was about 86%, and we also applied the two segment trapezoidal rule, which gave us 36.6%. If you remember, in the two segment trapezoidal rule, we also used these three data, and with the trapezoidal rule we got 36.6% error. But in this, with the same data, you can use this formulation and get much lower results, because we are actually using a second order polynomial. 16.6%, which is better, it shows. In the same example, we can also calculate the error actually. And if you remember, the true error was minus b minus a, 5 divided by 2880 f4 psi. And we don't know this psi, so instead of this, we use approximate error, which is minus 0.8. Actually, it's the same, b minus a minus b minus a, 5 divided by 2880. But in here we have, instead of f4 x, we have f4 mean x. Once we find it, we just plug this in here and continue. So for that we need the function, fourth order derivative of this function. If we take it, so let's take it here, not this one, but first we need the fourth order derivative, this one, like this maybe, of x. If you take the fourth order derivative of this, simply this becomes 0, this becomes 0, this becomes 0, because fourth order is like 3 times 2 times this becomes 0 as well. This one, 4 times 3 times 2 times 1, and x remains only. Sorry, not even x remains, only the value remains. So 4 times 3 times 2 times and 1 times, and actually let's make minus here, and 900 plus, for this, 5 times first derivative, 4 times second derivative, 3 times third derivative, 2 times fourth derivative, and x remains, 400 times x. So if we multiply these, f4 x is equivalent to minus 21,600 plus 48,000 x. So this is the fourth derivative, and for the fourth derivative, what we will need to do is we use the mean function, this one. Let's use that here. Let me write it in blue maybe. F mean for x is equivalent to the integration from 0 to 0.8 of the fourth derivative, this one, put it here. So minus 21,600 plus 48,000 x divided by b minus a, 0.8 minus 0. So mean means, this is the mean. So this is the mean. In integration, it is in between the limits. So when we solve this, it becomes minus 21,600 x and plus 4830 x squared divided by 2 divided by 0.8, and for this the limits are 0 and 0.8, so we put 0.8 into here and into here. The result here becomes minus 2400. So this value is minus 2400, then we can put it here now, and that means take EA here. Let's write like with black. EA is equivalent to minus b minus a means 0.8 minus 0 to the power 5 divided by 2880, and the mean value is minus 2400. And from here, the EA becomes 0.2730667. And in the previous slide, we also calculated ET. Here we can also calculate it if you want to, but we calculate it using the actual value, and ET was, if you remember, 1.640533 minus the integration value that we approximated through the Simpsons rule. It was 1.3674767. You can check the previous slide if you want to be sure, and the result was 0.2730667. Interestingly, the true error and the approximation error are the same, exactly the same. And maybe you can consider why, but the reason is simple. When you check the fourth order derivative, that's just a linear function. This is linear, and the actually error for the Simpsons rule is accurate for second order and first order and third order as well, because this is fourth order. So because the derivative is smaller than the third order, then it should give us exactly the same result as the true value. So when you have a function, and if its derivative that you want to use in the error, like f4 actually, fourth order derivative that you use in the approximation error formulation, if the derivative is in a smaller degree of that, then you will get exactly the same result with the true error. So that's the basic idea. And this is important because in Simpsons rule, we understand that we can get the true error with the approximate error, which is a very unique feature of this. You can also understand it from this one and this one actually, because h to the power 5, we have 5 here in the error, and this is fifth order function. That's why we will get exactly the same result. But if we had a higher function order than this, maybe 6, then we were not going to get exactly the same result. That's why maybe the derivative may not be true, because if we have the sixth order, this will be second order. Then according to my previous description, we would expect exactly the same. Actually, it's not true. So let's forget about the derivative, but think about this one. So the error has the fifth order here for h, and if it is fifth order and this is fifth order, then we will get the same result. But if this is fifth order, if the function is more than fifth order, higher than fifth order, 6, 7, doesn't matter, then we will not get exactly the same result. So check this if we are getting exactly the same result or not. So this is a good example to see the error in Simpsons rule. And Simpsons rule, 1-3 rule, is very unique because we get exact results for this kind of curves actually, or functions.